Modern high-performance electronics rely on highly ordered, complex material structures. Chemical sensors utilize zinc oxide, or ZNO, nanorods. Advanced supercapacitors require Ti3-AlC2 max-phase films, layered conductive ceramics, and electrocatalysis depends on gold, or Au, nanoparticles. These applications require materials deposited in perfectly uniform films that are merely 1 to 100 nanometers thick. Manufacturing at this scale requires a radical conversion of scale. To construct microscopic layers atom by atom, we must find a way to dismantle macroscopic, solid blocks of metal or ceramic. Standard atmospheric conditions make this precision impossible. Reactive oxygen, nitrogen, and airborne particulates would immediately interfere with the atomic lattice and contaminate the synthesis. Consequently, nanoscale structural fabrication requires an isolated environment where the kinetic behavior of every particle is strictly controlled. Radio frequency, or RF, sputtering provides the physical mechanism to achieve this atom-by-atom synthesis. This process transforms invisible, alternating electromagnetic energy into the precise kinetic physical bombardment of a target material. Two primary physical actors facilitate this energy transfer: a low-pressure process gas, which acts as the projectile, and a solid target material, which serves as our atomic source. Achieving precise atomic synthesis through these elements requires a tightly sequenced physical process of collision and ejection, engineered from the ground up. By controlling these collisions, we establish the specific physical parameters needed to dismantle a solid source and reconstruct it at the molecular level. The process begins inside a strict vacuum chamber. Total isolation eliminates ambient atmospheric interference, ensuring that only the intended elements participate in the film formation. The spatial orientation is fixed. The solid source material, the target or cathode, is positioned at the top, while the destination surface, the substrate or anode, sits at the bottom. Once the vacuum is pulled, a low-pressure inert gas is introduced. Argon is the industry standard due to its high atomic mass, which makes it an effective tool for physical displacement. The argon floods the space between the cathode and anode. In this baseline state, the gas atoms are electrically neutral and remain chemically inert. Without the injection of energy, the system remains stable and incapable of material transfer. To initiate the process, we apply radio frequency, or RF, power to the chamber. This creates a rapidly alternating electric field between the cathode and anode, fluctuating millions of times per second. This alternating field interacts with the neutral argon atoms suspended in the chamber space. The intense electrical forces of the RF field strip electrons away from the argon atoms, leaving the atoms with a positive charge. This ionization transitions the neutral gas into a highly energized heavy ion plasma. This plasma serves as the necessary kinetic engine required to displace and move solid matter across the chamber. RF power effectively turns a passive gas into a volatile, electrically charged medium ready to be directed at the target. A strong electrostatic relationship now exists between the positive argon ions and the negatively charged target cathode at the top of the chamber. Because opposite charges attract, the electric field accelerates the heavy argon ions upward, driving them at high velocities into the target surface. The ions strike the solid atomic lattice of the target material. The kinetic energy transfer from these impacts forces individual target atoms to break their internal bonds and detach from the solid. Having absorbed enough kinetic energy to break free, the dislodged atoms are ejected from the surface and become vaporized. The efficiency of this vaporization depends entirely on the mass and velocity of the incoming argon projectiles. Sputtering achieves material transfer through the brute force kinetic eviction of atoms via continuous heavy ion impact. The newly vaporized target atoms now follow a downward trajectory away from the cathode. Within the vacuum environment, these atoms travel unimpeded toward the substrate positioned at the bottom of the chamber. As these atoms strike the substrate, they lose their kinetic energy and condense. These atoms accumulate layer by layer to form a uniform, highly ordered film between 1 and 100 nanometers thick. The deposition phase represents the precise reconstruction of the destroyed target material into a new nanoscale structure. A baseline sputtering system faces a significant inefficiency. Free electrons rapidly scatter away from the reaction zone near the target. This loss of electrons limits the ionization of argon, which in turn slows the deposition rate to a trickle. To make this process industrially viable, magnetrons are installed behind the target material. This creates a magnetic field, confining electrons into helical paths at the cathode surface. Trapping them dramatically increases argon ionization, resulting in a much higher rate of atom ejection. This high-efficiency configuration is required to sputter complex, highly bonded materials, like nitrides and oxides, which demand intense kinetic bombardment. Magnetic confinement transforms sputtering from a slow laboratory phenomenon into a high-rate industrial process. The entire process forms a continuous mechanical loop. RF fields create plasma, ions bombard the target ejects atoms, and those atoms condense onto the substrate. While the system is powered, this kinetic cycle repeats aggressively, shifting material from the source to the substrate. Without the electron confinement provided by the magnetron, the plasma density would be too low for practical manufacturing. This perfected mechanical process is what allows for the creation of the ZNO sensors, Ti3-AlC2 supercapacitors, and gold electrocatalysts mentioned earlier. The performance of these advanced electronic devices relies entirely on mastering the specific vacuum physics of the sputtering chamber. RF sputtering represents the successful translation of electromagnetic theory into the precise construction of molecular architecture.